Hi, this is a lecture for Math 152, sections D100, D200, D300 for the spring semester 2020. As you all know, we have an exceptional situation on hand here where their live lectures have been canceled for the foreseeable future because of the coronavirus. So we are going to be the three of us, which is myself, Brenda Davison, and the two other instructors, Jessica Stockdale and Ben Adcock, will be recording lectures that you'll be able to watch and listen to. So this will sort of be going on a rotation. So I will do this one, and then Jessica will do the next one, and then Ben, and then we'll be back. And all three sections will be able to watch all of the lectures. So here we are. We're going to start with sequences. So a sequence is just simply a list of numbers. We've got to really keep straight the difference between a sequence and a series. It's my experience that it's easy to confuse those two. So for example, a sequence could look like this. Here's a sequence: 2, 4, 6, 8, 10, etc. That in fact is an infinite sequence, just a list of numbers, in this case the even integers. So a sequence has a limit. You can ask what happens as you keep going and going and going. And in this case, you could see that the limit would be infinite. And you could also ask what is the nth number in the sequence. You can ask those kind of questions. We're going to see how to handle those sort of things in this lecture. This is not to be confused with a series. So this one here, this is a sequence, a list of numbers. A series is a sum. So when we look at a series, the sort of equivalent with these kind of numbers, a series would look like this: 2 plus 4 plus 6 plus 8 plus 10 plus ... That would be an infinite series. So then we could ask the same kind of questions. If we add up n of them, the nth partial sum, what would that be? If we take the limit as n goes to infinity, what would the sum be, etc., like that. But we don't want to confuse when we're talking about a sequence and a series. Okay, so a sequence is a function whose domain is the set of positive integers. It is sometimes possible that that 0 will be included, in which case we will denote that the sequence is a list of numbers: S0, S1, S2, S3, etc., like that. So here, for example, we could try to write out the first few terms of the sequence, which we're going to denote this way: cos n pi, as n goes from 2 to infinity. So we simply take a look at the starting value for n, and we use that in the first in the function here that we're told to evaluate. So when n is 2, we would have here cosine 2 pi, and then when n is 3, we would have cosine 3 pi, and when n is 4, we would have cosine 4 pi, etc., like that. And that our sequence of numbers will be these numbers: cosine 2 pi, cosine 3 pi, cosine 4 pi, etc., etc. Okay, we could actually, because we can take a look at what the cosine function looks like. The cosine function looks like this, and we have, for example, 2 pi being right here, 2 pi, and we could continue the cosine function along like that. Where would 3 pi be? Well, 3 pi would be right here, and then 4 pi would be right here. So we could, in fact, evaluate cosine 2 pi, cosine 3 pi, cosine 4 pi, and write these numbers, write this sequence in a different manner. It would then look like this, a sequence that would look like this: 1, minus 1, 1, minus 1, 1, etc., like that. And it would sort of alternate between 1 and minus 1. And then we could, in fact, write that a little bit more compactly. That would look like this: minus 1 to the n, when n goes from 2 to infinity. We would get exactly the same thing. So in fact, even despite the fact that this looks very, very different, these two things produce the same list of numbers. So it's just a list of numbers, and we can sort of tell you how we can either list them out explicitly. That would be this way here, just list out the numbers explicitly, or we can give you one or more ways of generating the numbers from a more compact expression, a function whose domain is typically the positive integers, or can be specified in this manner. Okay, so we're going to just take another example here. Here's a sequence, and we're going to just sort of graph it and see what it looks like. So in order to graph it, what we're going to do is we're just going to calculate the first few values of the sequence. You notice that there's no indication of what numbers it starts and ends with. When that happens, you should assume that it's n equals 1 to infinity. So unless otherwise indicated, the domain is going to be the positive integers. Okay, so we can just make a calculation of A1. So what we're doing is I'm going to do this once in gory detail, and then I'll just write down the next one. So we're going to talk about n being 1. That's what this little 1 here. So we have A sub 1, the first number in the sequence, and we're going to calculate that by plugging 1 into this formula. So it's going to be 1 plus negative 1 to the 1 divided by 1. And I make that calculation, and I get 0. Well, maybe I'll do one more in detail. Then we calculate A2. And A2, so that's that we're again looking at this subscript here. That is when n is equal to 2. So then we go 1 plus negative 1 squared divided by 2, and we add that up, and that is 1 plus a half, and we get 3 halves. Okay, and then we do A3, same thing. Now we put n equal to 3, and we make the calculation. Maybe do just a few of them yourself, just to ensure that you agree with my arithmetic and that you understand how to generate these numbers that I'm doing here from the description, the compact description that we have here. Okay, so I calculated out A3 to be 2/3, then I calculated A4 to be 5/4, A5 to be equal to 4/5, etc., and then I just got very excited by this whole thing, so I just kept going. 7/6 for A6 and for A7, and then I can actually, without even doing more calculations, I can see it looks like there's a substantial pattern here that I could exploit. Okay, then I'm going to graph and see what this looks like. And so I draw a graph like this, and I am going to have the domain of the function. So the domain of the function is 1, 2, 3, 4, these positive integers here, for which I've made the function calculations. I'm going to draw a line here, maybe just a dashed line, even like this, dashed line of 1. So I can just get a sense on where these things are. So we just calculated that a of 1 is 0. So I'll just plot these in a different color so we can see what we're doing. A of 1 here is 0. And then we computed a of 2, and we got 3 halves. So let us think that this would probably be about 2. So here would be 3 halves. So a of 2 is going to be sitting right there at 3 halves. Then we do a of 3, which is 2/3, and 2/3 is approximately there. And then we go ahead. A4 is a little bit more than 1, 5/4, and then 4/5, and then what is it? It's kind of you can see what's happening here. It seems to be getting closer to this line. So then we could say, okay, we've got this list of numbers. Here it is, 0, 3 halves, 2/3, 5/4, 4/5, 7/6, 6/7, and we just keep going and going and going. And then we could ask, what is the limit? So what is the limit as n goes to infinity of an? And that is going to be the limit as n goes to infinity of the way that we're calculating an, which is 1 plus minus 1 to the n over n. Okay, and looking at this limit, you can see handily that this thing here is going to alternate sign, but as n grows larger and larger and larger, this thing is going to go to 0. So the limit is indeed 1, which is in fact what we saw happening on the graph, because that line is y equals 1. Okay, or I should maybe say this, if I was going to plot it this way, an versus n, and that is when the limit as n goes to infinity is that we would expect the number to get arbitrarily close to the line an equals 1. Okay. Alrighty. So sort of capture the definitions associated with what we've just seen. We have a sequence. There it is. We somehow tell you what it is, either as a list or in a more compact way, and it has a limit, L, and we take the limit as n goes to infinity. And what we mean is an approaches L as n approaches infinity. Okay, so we have a way of defining that. And if that limit exists, then we say that the sequence converges. And otherwise, if that limit does not exist, we say that the sequence diverges. Okay, so we have briefly talked about this in math152 D300, that we can be a little bit more rigorous on our ideas of saying what happens when something gets close to something else. And so the little bit more rigorous of a definition is here. This is not materially, this definition here is not materially going to affect how you actually do the computations, but sort of it is a nicer way of just saying, well, this gets close to that when that gets close to that, to actually formalize it. And the way that we do formalize it is to say that what we mean by the limit, what we mean, the limit is n goes to infinity of a n equals L. What we mean is that if we pick some any epsilon bigger than 0, typically it's very small, then we're guaranteed to find a large value n such that the difference between a n and the limit will be less than epsilon whenever n is greater than n. So that's the formal definition of the limit of a sequence. Okay, so let's take a look at an example. Here we have a sequence, 2n over n plus 3. Does it converge or diverge? Excuse me, I have a bit of a cough. Okay, so let us take a look at that. We will take the limit. The limit as n goes to infinity of 2n over n plus 3. That's going to be the limit as n goes to infinity, and I'm going to divide numerator and denominator by n and write it like this, just to make it easier to see what's happening. Okay, and at this point, it's fairly obvious that the 3 over n, when n gets large, goes to 0. So that goes to 0, and then you can see that the limit here is 2. That's finding the limit of a sequence. So then we would say this sequence is convergent. Is convergent. Okay. Okay, if we have a sequence, so this is our sequence where the domain here is the positive integers. Our domain here is the positive integers. Then what we can do is actually form the equivalent function where the domain here is the real numbers, or even let us just say the positive real numbers. And if the limit of the sequence approaches if the limit of the sequence approaches L, then the limit of the corresponding function, that the corresponding continuous function, also approaches L. We're taking that to be a theorem. So let's just take a look at what this means. And the reason it's important is because we can't say, for example, differentiate a function which is just defined on the integers. So what we basically do is expand it to all of the numbers and then differentiate it and then relook at what's happening just on the integers. Let's take a look at what I mean by that. Okay, here's our sequence. We have the values of our sequence like that, and we're perhaps curious what the limiting value is. And we have all these values like that. What we can do is then say, you know what, we're going to define a function which is the same on the integers as our sequence, but is also defined in between the numbers. So that would be this red line here. This red line here is f of x right there, f of x, a continuous function. And then our dots, these things here are our sequence, that is a of n. And our theorem is simply telling us that the limit as n goes to infinity on a of n will be the same as the limit as x goes to infinity on f of x. Okay, so sometimes we will turn it into a function so that we can use our tools of calculus to analyze what's going on. Okay. If we say something like this, that the limit as n goes to infinity of a of n equals infinity, it means that for any positive number m, we can always go far enough so that a n is bigger than m whenever we're far enough out. This is a divergent. This is a sequence that diverges to infinity. Okay, there's two ways of diverging. There's diverging to infinity, and then there's diverging via oscillating. Let's just make a note of that so we remember that. Okay, so if we have a situation, if a sequence diverges, then we can have two possibilities. One would be that the limit as n goes to infinity of an is equal to plus or minus infinity. So that's a divergent to infinity. And then we can have our second choice where we have the limit as n goes to infinity of an does not exist, but does not go to infinity. Okay, I'll just draw a graph. I mean, this is if you want to think, okay, but does not go to infinity. Okay, so you could be thinking of that, like, for example, in the continuous case, that would be something that looks like this. Like, so this say, for example, f of x equals sine x. The limit as x goes to infinity of sine x does not exist. However, it doesn't get really large either. It just keeps varying between -1 and 1. And in the same way we saw the sequence earlier, we saw a sequence, this one, cos n pi, where n was from 2 to infinity. And we saw that that was producing these numbers. What did it? Let's see, did it start with -1 or 1? Let me just make sure I get that right. It started with 1, cosine of 2 pi being 1. So we saw that this was these numbers here, 1, -1, 1, etc. This does not converge either. It diverges, but it doesn't get large. So it's exactly the same idea in the continuous case as it is in the case where we're just looking at a sequence of numbers. All right. Here's a bunch of facts about sequences. And so notice what our ground rules are here. We're saying if the sequence an and the sequence bn are convergent and c is a constant, then the following facts are true. So I'm just going to read through them quickly here, but maybe pause and take a look at these and make sure that each one of these things makes sense to you. So if we have, if we're taking a limit of a sum or difference, this one right here. If we're taking the limit as a sum or difference of two sequences, and then that is equal to the limit of each one individually. Okay, make sure that you understand that this condition must be satisfied. Otherwise, this is not true. Okay, so we're going to be cautious about that. We have the if statement here. These things must be true, and then all of these will apply. We can move the constant outside. All right, we can the limit of a product of sequences is the product of the product of the limits. The limit of a quotient of sequences is the quotient of the limits of the individual sequences, of course, as long as the one that's in the denominator is not 0. If we were to take the limit of a sequence where we raise each item to the pth power, then we could simply take the limit and raise that to the pth power. Okay, this is true only when p is greater than 0 and all of our terms are positive. If the limit of the absolute value is 0, then the limit of the sequence, which maybe all the terms are not positive, is also 0. If we have a third sequence here, Cn, that is between an and bn, and the limit of an and bn are both L, then the limit of Cn is L. This is the Squeeze theorem in this discrete case, Squeeze theorem. Some of you also know this by that, what I think is a horrible term, the sandwich theorem. Okay. We also just saw this. If our limit of our sequence is L and the function is continuous at L, then the limit of the we didn't actually see this. This is slightly different. Sorry. So if we've got the limit of a sequence is L and we have a continuous function at L, then the limit of as n goes to infinity of that function evaluated at the values of the sequence is the limit is the function evaluated at that limit. Okay, we're going to see how to use these things in some examples. Here we go. Show that the sequence square root, the nth root of n converges to 1. Or to do that one first. So what we're asking is, what is the limit as n goes to infinity of n root n? Okay, I'm doing example 10a here. That is, let me just rewrite that in a slightly different notation. That is like this: the limit as n goes to infinity of n to the 1 over n. Okay, so when I first look at this, I'm wondering what to do. I sort of try to get a grasp of what's happening, and I'm saying, okay, when n goes to infinity, clearly n gets large and 1 over n gets small. So to me, I'm thinking, okay, this looks like infinity to the 0, and that is an indeterminate form. So that would off the top trigger me to think, oh, maybe I should use L'Hopital's rule directly. But then I have to stop and be careful, because when I go to use L'Hopital's rule, I'm going to be thinking of taking a derivative. And now I have a problem because I don't have a continuous function. Okay, so let us note this. Can't use L'Hopital's rule directly. Why? This, if I wrote it this way, this function is not continuous. Okay, it's just defined on the integers. So I have a bunch of discrete points. I cannot take the derivative. Okay, so what do? I basically have to fall back on the theorem that says, oh, let me look at the equivalent function defined on all of the real numbers. Let me use that to figure out what's going on, and then let me go back and extract the data just at the integers. So what I do then is say, okay, whatever the limit is, this limit that I'm trying to find, it is guaranteed by that theorem we just saw previously that this will also be the limit as x goes to infinity of x to the 1 over x, where x is, I guess I should do it this way, x is are the real numbers. Okay, so now I have in this function here, a function of x, I have a continuous function that I can apply a derivative to. So let us now recall how to do that. So I now know that I have some limit L that I'm trying to find. It's the limit as x goes to infinity, x to the 1 over x. 1 over x. And when I see that sort of thing there, I've got some variable in the exponent. I immediately think, wouldn't it be nice to get that out of the exponent? How will I do that? I will use the logarithm function. So I'll take the log of the limit, and that's going to be the limit as x goes to infinity of 1 over x log x. Because the log function allows me to bring down the exponent in front of the log function. Okay, now I look at this. Now I see I have an indeterminate form, 0 times infinity. Okay, so that's fine. I know to use, I'm still thinking of L'Hopital's rule. I need to make this look like 0 over 0 or infinity over infinity. So I proceed to do that. That's going to be then the limit as x goes to infinity of log x over x. And now I have that indeterminate form, infinity over infinity. And then I can use L'Hopital's rule, which I'm going to just indicate like that on my equal sign. I'm going to take the limit as x goes to infinity. And I'm going to take the derivative of the numerator and denominator. So I'm taking the derivative of log x, I get 1 over x. I take the derivative of x, I get 1. And then now I can take this limit. I see, oh, it's getting, x gets very large. I'm 1 over something very large. This limit is 0. But let's not forget that that's the log of the limit I'm looking for. That's the log of L. And so then L must be e to the 0, which is 1. Okay, now we have that we have it done for the continuous case, and then we are extra careful, and we are saying because n to the n is equal to x to the x when n is in z, then the limit as n goes to infinity of n to the n is also 1. Okay, so you just don't want to be differentiating functions that are not continuous. That does not make sense. That's the new wrinkle from Calculus 1 where you have seen this before. Okay, let's look at the next example. We've got a to the n is equal to sine n pi by 2. Okay, so we're wondering what's happening here. And so let's just take a look at a few values. This actually should not be too hard to see what happens here. N equals to 1, that we're going to end up with sine of pi by 2, and that's 1. And then when n is equal to 2, we end up here with sine of pi, and that is equal to 0. And when n is equal to 3, sine 3 pi by 2, and that is minus 1. And then we see what's going to be happening here. N is equal to 4. We have sine 2 pi is going to be 0. And then we see by the sort of periodicity of the sine function, this is just going to keep going. It's never going to approach a specific value. So that means a to the n equal to sine n pi by 2 is divergent. Okay, and this is the second type of divergent. We indicated there was two types. One was going to infinity, and one is oscillating. This is the oscillatory version. Okay, let's keep going. So remember we're talking about, does a sequence converge? All we're talking about is we've got a list of numbers, and what happens to the number when we keep going and going? Does it move close to some finite number? That's what we're asking. It's just a list of numbers. Okay, 11a. Let's see here. We've got the limit as n goes to infinity of cosine n pi over n. I mean, I look at this and it seems readily apparent to me that the cosine is bounded above and below by 1 and minus 1. It's bounded below by minus 1 and above. So here's what I'm thinking, and above by 1. Right? For all values of n, I mean the cosine never escapes out of out of that interval, and n just keeps getting larger and larger and larger. So this thing is going to be 0, and it converges. If you're not happy with that little bit of potentially hand waving there, you could, in fact, it's a good exercise for you to try, formally set this up using this using the Squeeze theorem. There it is. Okay, then let us take a look at example 11b. For what values of r does a sequence r to the n converge? So we have a situation like this. A1 is equal to r, A2 is equal to r squared, A3 is equal to r cubed, and A4 is equal to r to the 4, etc., etc. And we're asking what happens when this number here gets very large. Okay, that is the limit as n goes to infinity of r to the n. And allow me to just give you a list here. Okay, so you have seen this before. This thing goes to infinity if r is greater than 1. Okay, so if we have, for example, 2 squared, 2 cubed, 2 to the 4, 2 to the 5, 2 to the 6, that clearly just gets extra large. So that is diverged to infinity. Okay, so that's the case for r greater than 1. It goes to 0 if 0 less than r less than 1. Okay, what do we have there? Well, that's a geometric series within its radius of convergence. Okay, so we're going to be coming to a lot of terminology about how to talk about convergence in this whole section in chapter 11. These two things you have seen before, section 2.6 of the Stewart textbook. It is equal to 1 if r is equal to 1. So that means let us just take a look at that. That is because the limit as n goes to infinity of 1 to the n is the limit as n goes to infinity of 1, which is equal to 1. Actually, I should be just slightly careful here. I realize I used the word series, geometric series, but we're not actually looking at the geometric series. We're just looking at the list of numbers. It is true that if you were to add them together, they're a geometric series, and in fact, geometric series would also be converging here. But that's actually, I want to be careful. I'm saying we're just looking at the numbers. So if for example, and we're in this range and we have something that looks like this: 1/3, 1 1/9, 1/27, etc., like that, that is going to go to 0 as the denominator gets large. Okay, that's what we're looking at. We're not adding them together. We are simply making a list of the numbers. Okay, it also goes to 0 if r is between -1 and 0. We can just actually make an immediate claim. That's because, a shorthand notation for because the limit of n of the absolute value, we've already seen that one, is equal to 0. That implies that that symbol there implies that the limit as n goes to infinity of an equals 0. Okay, and then there are a couple of more categories here. Allow me to expand down my case statement. It diverges if r is equal to -1, because we just go -1 plus 1 -1 plus 1, and it diverges if r is less than or equal to -1. So I could now summarize this. So I've gone through and kind of in cases and analyzed them all, so I can in these particular cases get a handle on what's happening, and then I can combine that whole thing into a much more succinct statement that looks like this: r to the n converges -1 less than r less than or equal to 1. So those are the values of r for which the sequence converges. Notice this. Okay, they're different. Okay, one is less than and one is less than or equal to. Okay, just a little bit more notation, definitions, notation and vocabulary. Please make sure that you understand what the words mean, so that when we use the words, you understand what we're talking about. It's really important to have the vocabulary clear in your head. Okay, so we call a sequence increasing, right, like that. An plus 1 is greater than an for all n bigger than or equal to 1. That basically means, so an increasing sequence would be like this: 1, 2, 3, 4, 5, dot, dot, dot. That is an increasing sequence. Okay, each one is bigger than the previous. Okay, it's decreasing if it's the other way around. Here's a decreasing sequence: 100, 99, 98, dot, dot, dot. That's a decreasing sequence. Okay, in this situation where each term is either increasing or each term is so in this condition where each term is larger than the previous one and it's increasing, or in this case where each term is smaller than the previous one and it's decreasing, if either of those conditions are satisfied, then we call it monotonic. Okay, what does it look like to be not monotonic? For example, this is not monotonic. That is neither increasing nor decreasing. It's a list of numbers. Sometimes it's going up, sometimes it's going down, sometimes it's going up. That is not monotonic. Okay. So we're going to take a look at these sequences here. Is it increasing, decreasing, or neither? So let's take a look at 13a. Let us take a look at the terms. We have 1 plus 1 over 1. We have 1 plus 1 over 2, 1 plus 1 over 3, 1 plus 1 over 4, etc. It keeps going. Let us do the arithmetic here. We get 2, and we get 3 halves, and then we get 4 thirds, and then we get 5 quarters, etc., like that. And it is indeed decreasing. We can see this, but we're going to be a little bit more sophisticated in our analysis, but for now, let us just say we can notice an plus 1 less than an, and then we conclude it's decreasing. Okay, let us though imagine that we didn't want to write out a whole bunch of numbers and then see what's happening. Could we somehow do it a little bit better? So let us take a look at an. Now I'm thinking to myself, looks to me like an, or maybe I would just guess or something like that, an plus 1 less than an. And then I would write out what that means and see whether indeed I've got a true statement. So let me write out, what is an plus 1? Well, that is 1 plus 1 over n plus 1. I'm sort of in some sense wondering if this is true. And what is an? That is this. Okay, so now on both sides, I am going to form a common denominator, and I'm going to get this here, n plus 2 over n plus 1. And I'm wondering, is that less than n plus 1 over n? Okay. Then I am cross multiplying, and I'm getting n times n plus 2 less than n plus 1 squared. I'm going to expand, and then I'm taking a look, and I end up here. I can cancel some stuff here like that, and I get 0 is less than 1. That is a true statement. So now what I could do, in fact, is start here. 0 is less than 1. Make this claim is this is then true, this is then true, this is then true, this is then true, and indeed this is then true. Okay, so I have now assured myself that this is a decreasing sequence. Okay, 13b. Let's take a look at 13b. It looks like this: 1 minus 1 over 1, 1 minus 1 over 2, 1 minus 1 over 3, etc. 1 minus 1 over 4, and I can keep going. That I'm going to get 0, then I'm going to get a half, then I'm going to get 2/3, I'm going to get 3/4, etc. like that. Indeed, it looks to be increasing. Okay, you could do exactly the same thing. Then what you want to show, so you want to show that bn plus 1 bigger than bn. How about you do that as an exercise? I expect that we'll be posting completed lecture notes here for you guys. So that is increasing, and you could show that as an exercise just like I did on the previous one. Okay, let's take a look at 13c. This one's easy to do because as soon as you see in the first few terms that things are not going either always going up or always going down, you can immediately stop and make the conclusion that it's neither. So let's take a look at the first one and the second term. There's the second term, and then the third term. The third term is 1 plus minus 1 cubed over 3, and I'm just going to keep going. And let me rewrite those with the numbers. I'm getting 0, and then I'm getting 1 plus a half, which is 3 halves, and then I'm getting 1 minus a third, which is 2/3. So I see it goes up in this direction, and then the next one, going between these next two, it's going down, and then immediately conclude neither. It's not monotonic. All right. Another definition, bounded above. That means there's some number m which is bigger than all of the terms in the sequence. Bounded below, some number small m which is smaller than all of the terms. If it's bounded above and below, then it's a bounded sequence. So you just sort of imagine from a graphical perspective, if I have a sequence and the numbers kind of they look like this. There doesn't even have to be much of a pattern, but none of them get bigger than this, and none of them get smaller than this. All of the numbers that we get, all of the A1, A2, A3, AN, all of them are between little m and big M, then it is a bounded sequence. Okay, coming an important theorem that we'll be able to make use of, the monotonic sequence theorem. If the sequence is bounded and it's monotonic, then it converges. Okay, so in this case, a nice little example, you can see it's bounded above by some number m, and then it is steadily increasing. I mean, what else could possibly happen in a sense? Like it cannot get bigger than m, and it's increasing. So therefore, it has to have some sort of limit, and um, that is what this theorem is telling us. It is convergent, and there is some limit L. Okay, so we're going to use that fact in our last example for this lecture. That would be this one here. Let us take a look at a sequence that is defined recursively. And what does that mean? Recursively means that we're defining an plus 1 in terms of an, not in terms of n. Okay, so this is this thing here. We're defining our sequence recursively. And this thing here is called a recurrence relation. So we called a recurrence relation. Okay, so let us first get a sense that we understand how to write out what the terms are. So we're told a1 is equal to root 6. There it is. So now we can compute a2. Now a2 happens when n is equal to 1. And we're told we should take the square root of 6 plus a n, and n is 1. So this is here the n equals 1 case. We know what a1 is. We just computed that. So that's going to be the square root of 6 plus the square root of 6. And I've got some numbers here. Let me just sort of write them over here. This one is approximately 2.449. This one here is approximately 2.9068. Okay, and now we want to calculate A3. A3 is going to be when n is 2, because 2 plus 1 is 3, and then that's going to be the square root of 6 plus A2. But we already know what A2 is. A2 is the square root of 6 plus the square root of 6. It's quite a pretty looking little thing here. And I calculated that one out, 9,844, etc. So what you see is happening is we're using A1 to build A2, and then we're using A2 to build A3. And this is what we mean by recursion. Okay, one final one, we'll calculate A4. A4 will be the square root of 6 plus A3. We have calculated A3. You could maybe, why don't you fill this in, and then check yourself using this number here, 9974. Okay, we can just keep going, etc. Then we're going to ask, we are asking, no, the word investigate here maybe not particularly prescriptive, but what we're basically wanting to know is what happens when n gets large. So that's what we're by investigating. What happens? N approaches infinity. What is going to happen? It looks like here maybe it's going to approach 3, but it's not so obvious to look at this column here and see does that actually approach 3? Okay, so what we're going to do is use a technique called mathematical induction. I know that some of you are also taking Macam 201, where you've talked about this. If not, certainly you could look up how to do mathematical induction, or you can just potentially follow this proof and see how it works. Maybe because I have extra time in a video, I will tell you the sort of Cole's Notes version of how this works, and that is we're attempting to show something for a large value of n, and so what we want to do is basically show, and I'm considering it like this, we show it true for n equals 1. Now we're going to have a domino representing n equals 1, and then we're going to have a domino representing n equals 2, etc., like that, and we keep going with our little dominoes, and this would say, for example, n equals k, and then n equals k plus 1. And our idea of what to do is to show directly, typically just by direct calculation, show that this one is true. That's our step 1. Step 1. Show that, and we call that the base case. Show that the base case is true. And then actually what we do next show that if this one is true, if the case is true, then that implies that the k plus 1 case is true. Now let's think about what that means. That means if I manage to show this scenario, that when n is k, then that forces n to be k plus 1 to also be true, that's telling me that if k is 1, then 2 must be true. And if k is 2, then 3 must be true. And then if k is 3, 4 must be true. So basically what I do is I establish this to be a big, strong domino. It is true. And then I show that this domino can knock over that domino, and then that domino can knock over that domino, etc. And then the whole thing flattens down like this, and my proof is complete. That is the basic idea of mathematical induction. Let us see it in this case. Okay, so I want to first show the sequence is increasing. That's what I'm going to do by induction. This is via induction. Okay. My method here is to show the sequence is increasing, and then show that it's bounded, and then I'm guaranteed that there's a limit. So the first thing to do is to show that it's increasing. I'm going to do that by induction. So what do I want to show? I mean, I have the idea that it's increasing from looking at this here. So I want to show that that's actually true. Here I only have a few cases. I can't assume that, you know, somewhere when n is 50 or something, it doesn't suddenly start decreasing. Okay, I don't know that. So I'm gonna show that the sequence is increasing. Okay, so that means what I want to show is that an plus 1 is bigger than an for all n greater than or equal to 1. Okay, so I'm going to take a look at when n equals 1. That's our base case. Is it true when n is equal to 1? Well, we've already made the calculations. Handily, we've already made the calculation. So it is true when n equals 1 because a2 is bigger than a1 as above. We made the calculation. Calculation is true. So then the next step, so this is here's my proof here. Proof, let me see. Okay, I'm going to change this to proof. Proof. Okay, then I'm here, base case. Base case, that's step 1. Step 1 of my proof. Step 2 of my proof. Assume the kth case. Assume it is k. Assume it is true for n equals k. What does that mean? That means I'm allowed to use this statement. Okay. And now I want to show that from this, now the idea is from this statement here, show that ak plus 2 is greater than ak plus 1. Okay. Then that will cause all the dominoes to fall down, right? I've basically caused I've said, okay, I can teeter over the first domino. Now let me make sure that when the first domino teeters over, it hits the second domino. That's the step I'm in right now, trying to show that the first domino will will knock over the second domino. Okay, first domino is easy. I've showed I can push over already directly. Okay, how do I do that? Well, I start with what I know. There's what I'm allowed right there, and I add 6 to both sides. I'm using valid algebra now just to proceed. There I do. I add 6 to both sides. I'm allowed to do that. That doesn't change the inequality. And then I can take the square root of both sides. There it is. And then I look at that and I'm like, hey, using the recurrence relationship, what is this thing right here? That is, in fact, precisely ak plus 2. And this one here is precisely ak plus 1. So I've shown that if this one is true, then this one is true. Therefore, it's true for all n. So I have now I've proved, in fact, via induction, true for all n. So I've shown by induction that the sequence is increasing. That was I sort of have a big step 1 here, show the sequence is increasing. There's 2 sub-steps. Now, part 2 in the big steps here, is it bounded? bounded? I'm now asking myself, is it bounded? Let us think, is it bounded? Is it bounded above, or I need to check bounded above and bounded below. Okay, so it is bounded below by 2. Okay, I mean, I know this because I see 2 is smaller than the first number, and I know it's increasing. So for sure it's bounded below by 2. Then so that's tick, bounded below. Bounded above. This one's a little bit more tricky because I don't actually know. So I go again into my induction model. I notice that I'm trying to say, is it bounded above? So I'm going to pick some number that it looks to be a bounded above by. In this example, I'm going to pick 3 because it looks like my numbers are lower than 3. I'm going to say, I'm wondering, is this thing bounded above? It looks like it's bounded above by 3. Let me prove that. So this is going to be a proof an less than 3 for all n. So let's take a look at, I do the same thing. Base case, a1, well, that's less than 3. I mean, we know what a1 is. Let me just scroll back. A1 is 2.44. It's clearly less than 3. The base case is true. Direct computation. Okay, next, assume AK is less than 3. Okay, so we basically got ability to teeter the first domino. Now let's see whether teetering the first domino will bonk over the second domino. That's our idea here. We're going to assume the kth case, and then I'm going to do the same thing. I'm going to add 6 to both sides. I'm just using valid algebra. Now I'm going to take the square root on both sides. Okay. And then let me just actually, to be a little bit nicer with the notation, let me just leave that like that, square root of 9. Okay, I've taken the square root on both sides, and then I look and I say, what is this thing? Oh, this thing is actually AK plus 1, and the square root of 9 is 3. Okay, so now I've said if the kth one is less than 3, then that forces the k plus 1 first one to be less than 3. That means they're all greater than 3. I mean, sorry, all less than 3. So therefore, the sequence is bounded above by 3. Okay, a bunch of work, maybe possibly a new idea on how to prove things via induction. So, okay, what do I have now? I have an increasing bounded sequence. Good news. It has a limit. Okay, so let's now figure out, see if we can figure out what that limit might be. So now I'm taking a look at the limit as n goes to infinity of an plus 1. Okay, let me say a couple of things. What the limit I'm looking for, L, is the limit as n goes to infinity of an. That is the limit I'm looking for. And we have the situation where an plus 1 is the square root of 6 plus an. Okay, so here we are, the limit. So now I'm taking, okay, I have this situation, and I know what now I'm going to take the limit on an plus 1. That is the limit as n goes to infinity of the square root of 6 plus an. Okay, and that is going to be equal to the limit, let's try that again, that is going to be equal to the square root of the limit as n goes to infinity of 6 plus an. Why can I do that? Flip back to the list of things, the properties of sequences that we had. The square root function is continuous, so I can move the limit from the outside to the inside or from the inside to the outside. That's because of the continuity of the square root function. Okay, then I proceed here, and I have here, then the limit as n goes to infinity of 6 is simply 6. So then I've got 6 plus the limit as n goes to infinity on an. And over on this other side, I still have the limit as n goes to infinity on a n plus 1. Okay, I have given this thing here, the limit as n goes to infinity of a n. I've given that a number. I know it exists. Some number L. I can do that because I've established from the fact that it's increased and bounded that there is a limit. Okay, so then I can replace that here. That is going to be the square root of 6 plus L. Okay, I'm really making a lot of headway actually. Let us look now at this. What is that? I mean, if n goes to infinity, so what my claim here is going to be that the limit as n goes to infinity on a n plus 1 is exactly the same as the limit as n goes to infinity on a n. We're saying there's going to be no difference between these two things because n is getting arbitrarily large, and this little plus 1 is going to make no difference. So both of these things, in fact, are L. Yeah, or you can maybe like write it this way if you like. Since n goes to infinity implies n plus 1 goes to infinity. Okay, so I can simply replace this guy here with an L, and then I have L is equal to the square root of 6 plus L. That allows me to solve for L. I square both sides, and I get L squared minus L plus 6 equals 0, and that factors in this manner equals 0, and we get here L equals 3. We know the limit is positive. It is bounded above. It's bounded below by 2, so this solution does not tell us anything, and it's bounded below by 2. We established that, and we now know what the limit actually is. So the limit as n goes to infinity of a n is equal to 3. This concludes the lecture for section 11.1. Thank you very much.